Welcome to another video of the Cubesat design and build. So in the last video we discussed about the software architecture of this firmware of the flight software basically. So I discussed about the world engine, decisions, power systems. If you have not watched that, it will help a lot to know where we are at this point. So in this one, I'm gonna make it short, and we are going to write some few template code or something like that for one of these systems. So I don't know which one I'm gonna write for yet, but this is obviously not the payload engine. I've not even designed that part yet. Comms and telemetry. Let's see. Maybe comms gonna be simple. So power system, that's not done. Designing or BC, decision engine and core FSM. This one requires these others, so I don't want to do that. Let's try something to do with the world engine for now, right? So what I'm gonna do, I'm going to open Notepad, Notepad++, right? So new file. Okay. So I'm gonna call this let me call it, I don't know, thoughts maybe. Dots. Project shadow flight firmware playground. There should be a playground somewhere here. Let me call it scratch. So I like to put my thoughts in a single, the raw ideas in a single file, so that I can figure it out as I go. So just to mention that I've not even thought about what's going to be like, but based on our hardware, I think we can come up with something. So I've opened the EZDA project here. Where is it? Project shadow flight hardware, this one, right? I'm gonna open the sensor board, combine schematic, ADCU, and see what we need to do here. So we have the power, obviously. We have the MPU 6050. Let me put it on that side a little bit and start with this side. So right now I'm translating the hardware into what functions I need in the firmware. So for voltage, one thing that I might need is to read, I don't know, let's see, read board voltage, right? Then we're gonna do something like, we have an inhibit switch here, so we're gonna say read inhibit switch. Okay, and then we have to turn the board on or off. So I have not added this MOSFET, but once I add it, I'll be able to control it from the OBC. So how do I call that? Activate board, right? Activate board. The next thing to do with power is this part, or this board insert is read from the OBC. I don't need that from this side of things. Enable pin is fine. Activate board, that name doesn't make sense. Turn board on. Let's just separate it. Let's say activate board, and then deactivate board. Doesn't matter really. They are two separate functions. So one thing, when I'm writing such firmware, I like to make things as simple as possible. There's a way, of course, you can have one function that does this thing, but just be as simple as you can. It does the job. It's better for everyone, for yourself too. right? So the next bunch of very critical stuff is the sensors, right? We have the MPU 6050. So what we need to do is write a driver for that. This is gonna be a whole separate thing, right? MPU 6050 driver, magnetometer. I just call it magnetometer driver. Let's see GPS. So we need a GPS driver. So remember that I mentioned that I'm gonna make this software or firmware as modular as possible. So everything is an object, everything is just a driver, right? So that it can be easily changed or improved or something like that. A DXL driver. This is a very critical part when you're mapping out a huge code base. So that's why I'm taking some few minutes for a start to do this. So there are the sun sensors here with ADC converters. This is a driver. So I'm gonna say sun sensor. Let's see. So you have two ADC converters, right? And they are I2C. So what I need to do is they are the same. So is have the same object, but that takes two different addresses. Yep. So I can create two instances of the same object, but the constructor can take two different addresses. Okay, I think that will be fine. So ADC driver, let's say sun sensor driver, right? So because I'm using C as a language, most of the OOP stuff is like not existent, which means we'll have to write our own version of it, or a modified version of OOP, which is not a lot of work to do in C. Yep. So what else do I need for this board? This is a sensor board, and remember, all of this data is going to be sent to the OBC through I2C, right? I think this is enough for now. Obviously, we are gonna get a lot of other functions as we go on, right? Now this board does not have its own MCU, so it means everything we read is gonna be packaged into an I2C packet, then sent to read by the OBC. Yeah. Now remember when we said that each of these functions are going to be tasks, right, or applications, that there are specific tasks that does the job. So what I'm gonna do is use RTOS obviously for that purpose. Where is it? Yep. Okay, so let's fire up our STM32 cube IDE for that purpose and create that. Oops, I already have it open. Let me open it. Okay, close this project, create a new project. Right, so our STM we are going to use STM32F401CCU6 F401CCU6. This is the first part. Next, I'm gonna call it ADCU. So my idea is to create a board separately, right? And then at the end I will compile all of these different board softwares or firmwares into the main board. I don't know whether so for example, the ADC is dependent on the OBC, right? Because it's sharing the MCU with the OBC, but I need to write it as if it's running on its own MCU for testing purposes. So I'll test the ADC and then test the OBC separately as well, and then combine them if they work fine. So I'm gonna call these Shadow Flight World Engine, right? It's not the default. Let's browse and go to our project. Where is it? Firmware. I'm gonna call this World Engine isolated, right? Or we call it this. I like to call these projects the same name as the name on the STM. So Shadow Flight World Engine isolated, right? Select this folder. So I'm gonna name this the same, use C, and everything is default. Then we generate that project. Generate that project. Right, here we are. So let's see. Okay, so the first thing that we need to do is initialize these guys. So the first thing is SDSCL, which is the I2C. So I want to make this very easy to integrate at the end. So I have to check which I2C I'm using on the OBC part first. This is PB6 and PB7. So it means PB6 and 7. This is I2C1. So connectivity I2C1, I2C. Right, that's fine. Next we initialize. So I2C takes care of this magnetometer, accelerometer. What else is using I2C here? And these converters, right? These two converters. So the other thing is the DS18B20 temperature sensor, which is going to, have I put it here yet? Not yet, right? So it's not assigned. So what I'm gonna do is use a global net here and call it this is DS18B20, right? I'm gonna remove that, put this one here and do that. So I'm gonna copy that and assign it to this pin like that. So this is P8, which is an input. P8, where is P8? P8 is right. Where is it? P8. Here it is. Is an input. And then we're gonna label it. I don't like why this thing is opening the GPIOs. It should be off by default. This is DS18 B20. Right. Next is GPS. This is PA9 and PA10. I think that is I2C 2 or 1. No, not I2C. USAT 1, right? So USAT 1. It has a conflict with PA8, but PA8 is USAT 1 CK, which I'll not be using, so it will still work fine if I use a synchronous mode, which is totally fine. So I'm gonna rename these ones to match the schematic. PA10 is connected to GPS TX, right? Because it's an RX on the chip. So this is GPS TX, and this other guy is GPS RX, right? I saved without finishing. Anyway, you can always go back and change it. So it generates the code to do with initialization of your peripherals, but let me finish it first. Next is, let's see what else we have. So we have this sorted out, these guys are sorted out. What else do we have? Magnetometer interrupts, right? We have this and that. So where are those connected? Mag int, here they are on the OBC. So mag int trigger, is this an input or an output? Let's see, I'm not really sure about that. Int trig, there's int trig and there's int, right? Well, the best place to check for that is datasheet. So I think I have datasheets somewhere here. MLX, do I have MLX? I don't have it. Okay, let's open it here, copy the part number, go to Chrome. Where's Chrome? Chrome is right here. Go to LCSC, paste this, and then open the datasheet. We check which those two pins, what they mean. Pin out. To see this is optional, right? Then int, is there int? Have they described it really? Int here, right here it is. It's also optional, but I want to know if it's used. What is it for? Let's do that really quick. Functional diagram, description. I want the. Where is that? Where do I get that information? Let's see. Okay, external trigger allows external trigger events to be set to 1. So it's more of an input. When it's set to 1, the acquisition will start. Acquisition will start with the external trigger pin. When external trigger pin detects a high value, acquisitions will continue to be triggered until. So it's not necessary really at this point, but we can use it. Let's check. I'm just scrolling through to see whether I can get it. Right. Okay, glossary of terms. Okay, this is not helping. Okay, cool. So for now, I'll use a mag int only. Right, so just connect these two. From that point, you know what? I did a very bad thing here. I'm not supposed to change. Where is it? This one. I'm not supposed to change this. Why do I forget? I'm not supposed to change this to a global net because I'm using the ISA connector, right? So everything is interconnected by default through what? Through this, right? So it is fine that way. Okay, so let's see. Mag int is PA8. No, this is supposed to be DS18, P20. Which other pin is not being used? PA15. Let's put it right there. Mag int is PA3. That's an interrupt pin, so from the accelerometer, so it's an input here. Mag int. I keep saving this thing. Next is mag int trigger PA2. I won't use that for now. Flash, this is the OBC, is not in the ADCU. What else do we need? GPS. Let's look about the GPS. We have RxTX. PPS is a pulse per second signal from the GPS to the OBC. So on the OBC, it's connected to PA1, right? PA1 is on this side. PA1 is right here. GPIO input, right? So I'm gonna call it GPS on PPS, or rather PPS, like that. Next is what else do we have on the GPS side of things? Activate. So activate is to turn on or off the GPS, which pin is that? GPS activate is P0. So it's right here. It's an output because we want to use it to turn on the GPS or off, right? On or off. So it's supposed to be an output. If I forget, I'll save this thing again. I'll just stop. Let's see. ADCU. I'm moving as fast as I can here. GPS reset, right? So where is reset connected to? Is it connected anywhere even? No, it's not. So we can connect it to this free pin. This is going to be GPS reset. GPS reset. Let me rotate it. Put it right about there. GPS reset. Okay. What else do we have on the GPS side of things? We have this, that. I2C is fine. So you see, you have two communication methods. We have the RX, we have the UART, we have the I2C. We can select either. So it means I'll have some form of flag. I should have some form of flag that activates maybe GPS sets, I2C, GPS set UART, right? Whichever works, we'll figure it out in the software. The other thing is I think everything is sorted from this board. I2C takes care of almost everything. So MOSFET. So this MOSFET will just be toggled on and off. Inhibit switch. What do we do about this? We need to know whether the switch. No, it's fine. I'm just overthinking. Cool. That's fine. So that's all we need. We have mapped. We have checked. We can now. Let me activate the clocks also. System core, reset, and clock controller, ceramic external. Then we need a way to debug. So these ones are conflicted with PA13, I think, is it? If I'm not wrong, PA13 is the one that is yeah, this is SDIO. So I need to change this pin from P13 to which other pin is free on the OBC. P13. How did I not see this? This mag int P3, not 13. I read that thing wrong. P3. So we reset this. Then we set P3 to it's mag int, so it's an input. User label is mag int. Save it. Oh, there's one thing I forgot to do. I forgot to activate the RTOS middleware. So just go back here. The way you activate RTOS is you come here to middleware and software packs, choose free RTOS. Then I'm gonna be using CMC's version 1, right? And then there's a whole bunch of things you can do down here to do with semaphores, timers, tasks, queues, everything that normal RTOS has. But I don't like to use this configuration tool. I'd rather write it from the software side, just hard code it for some reason, I don't know. So I'm gonna save it, and then you can see these two errors. RTOS is recommends to use a HAL time base rather than SysTick. So what I'll do, I'll come back here and then activate timers. No, on the, where is it? It's this clock, is it here? No, let's see system. Yeah, system time-based source. You choose this to be something else rather than SysTick. So I always use timer 1. It has always worked, but I think you can use any other timer that you're not using in the software side. So I'm gonna save it. I ignore this reentract this thing. I'm not going to be using a lot of printf and scanf stuff that usually bring problems with reentrance and stuff. So just generate it as it is, and let's see what happens. All right, so the next thing that I like to do is enable floats. So they're not enabled by default on STM. So you come here to project properties, build, C++ build, settings. It's usually in the settings, MPU settings. Use float with printf, new lib none, apply and close. So that will enable us to use things to do with things like, you know, just basic float stuff, right? Float stuff. Cool. So let's see what we have. Here's my notepad, ++. Yep. So we have the read board voltage, we have inhibit switch read, activate board, etc. So to read the board voltage, we'll be using an ADC, right? For now, I won't do the soft hardware. I'll just write that task, and FreeRTOS creates for us a default task. So for a task, there are 3 things you need. You need the task handle, you need this prototype, right? And then you need the task itself, this one, right? Those are the only 3 things you need for the task to create a successful task. So what I'll do, I'll create my tasks here, user code function prototypes. So what I want to do is I want to call this, I want to start it with world engine. That's going to be the baseline start name for any function or variable I'm going to use. So world engine what? Read board voltage, right? Task. So tasks always take pointers to arguments, void arguments. So in case you want to pass arguments, So that's gonna be that, and then handle, right? So we are gonna create task handles. So let's write that and say world engine, no, OS thread, OS thread ID, board, say I'll make this one shorter, board voltage read board voltage task handle, right? So I'm going to open this in a different screen so that it becomes easy to reference. This notepad, just open it right here, and so I need this, I'm gonna copy that, paste. Then what else are we reading? Read inhibit. I'm reading the inhibit switch. Read inhibit switch task handle. The other task is activate board. This can be a single function, does not have to be a task, or we can create a task, activate, then delete it, right? Activate board task handle. The other thing is deactivate board. Deactivate board task handle. Deactivate board. Then we have the MPU 64 driver. That is gonna be a separate thing. So what you can create is the read MPU 6050, right? And then we can have read magnetometer. And then ADXL. Read ADXL. Okay. The other thing is the sensor driver. Read sensor drive. Read what? Read sound sensors. Read sound sensors task handle. So what I'm thinking is also the world engine will have to monitor tasks, so we can have things to do with OS thread ID, monitor tasks, handle, monitor, how do I call it, monitor tasks task handle, something like that, right? Let me minimize that. All right, so this is 51 to 59. These are 8 tasks. I don't know, around 7 tasks. 1, 2, 3, 4, 5, 6, 7, 8 tasks. Right, so let's create them down here. This video is getting longer than I wanted. I want to 2 more minutes and I end it, and then create a part 2 for this as we continue. So I'm gonna save this. I'm just gonna stop, and this is part 1. To continue, you'll watch part 2 so that it becomes easier for me to edit and retouch it and export also later. Right, so I wanted it to keep it as short as 35 minutes so that at least we did not do a lot of coding, but we set it up for a start. So I'm gonna pick up from exactly here next time. Cool. Let me stop this guy. Stop.